All right, hey y'all, it's Miss Summers with your notes today on the scientific method. So today is the 24th, it's a Monday, it's our first asynchronous day, so we're not necessarily going to talk to one another in person today, but I wanted to make this so that y'all had a little bit of explanation behind the slides that you're about to see, okay? So you already saw our objective on the canvas, that today we want to be able to describe the steps of the scientific method and also explain the importance of each step, why each step has to be done, okay? I do need you to take notes during this. It's important that you write this down in some way. However you take notes, it's going to be up to you in the end, but it's not enough just to sit and have this video on in the background, all right? Make sure you write stuff down. So that way it's a little easier for you to come up with questions. All right, so we're going to start by explaining what the scientific method is. All right, so if you're writing notes, you can pause at any time, go back, you can write everything down and then go back and listen. It's up to you. It's up to you. We'll figure out how it works best for you. But what the scientific method is, it is a way, all right? When I started teaching science years and years ago, I would tell my kiddos, as I'm telling you today, science isn't really a thing. Science is a way. It's how you figure out something, okay? It's a method. It's a process, okay? So it's how you get valid answers to scientific questions. And those answers are obtained through observations and experimentations. Valid, in this sense, when we say a valid answer, we just mean a true answer, an answer that reflects reality. So, for example, if I were going to the doctor because I think I have the flu or something like that, all right, and they give me the little flu test up my nose, all right, if that test is valid, that means that whatever the results are actually what is happening in reality. Okay, so if the flu test says I'm positive for the flu, it means I actually have the flu. That's what we mean by valid. True. Okay, so there's 7 steps to the scientific method. Here they are. What I would recommend you do if you're writing down these notes, I would write these down, put a little space, couple spaces in between each, so you can jot some notes down. All right, so if you want to pause, jot them down, go ahead and do that. All right, and we're back. So let's look at the importance of each of these steps. We're going to start at the beginning. That's always the best place to start, at the beginning. So the first thing you do when you're embarking on this science journey is you're going to ask a question or make an observation. All right, an observation is something that you can sense with your 5 main senses. So you see something, you hear something, taste, smell, touch. Those things are observable, all right? The reason that we start with observations and questions is so that you have a purpose for your experiments, all right? Without a question, you can't figure out the answer. So let me give you an example, okay? Let's say I work for a pharmaceutical company, okay? And I spend all this money and all this time making a medicine. But I didn't ask the question, what is the medicine going to fix? What is the medicine for? Well, how am I going to know if the medicine works if I don't know what it's for? I had to ask a question first. How do I cure the cold? How do I cure the flu? How do I cure COVID-19? All right, you have to have a question to guide you. All right. So I'm going to give another example an example of a question that I might ask. Okay, I grow tomato plants. So I might look at my tomato. I see that my tomato plant is not doing well. It's kind of all brown and wilty and kind of sad looking. I might say, what would the best thing be? What could I water my tomato plant with to make it grow better? How can I make my tomato plant grow better? My tomato plant's not doing well. That's my observation. What can I do? That's my question. All right, research. This is a step that we don't really focus on as much in high school, but like if you go to university, this would be a big deal. Like you would have whole classes on like, how do you research? That's cool. But it's basically seeing what other people have said about your topics. So going back with my tomato plant, I asked, what can I give my tomato plant to make it grow better? So I would go through articles or journals or whatever, and I would look up, plant growth, tomatoes, and I would see, oh, this person says that adding, this brand of fertilizer. This person says water it with Gatorade. This person says salt water. Give you an idea of what other people have found. All right. Good research is from peer-reviewed sources. I won't get super deep into that. It just means that other people have read it and checked it and made sure that your experiment was good before it was allowed to be released to the universe. It's always a good idea to get research from many places, from multiple sources, because if you find 10 different people that all had the same question and they ended up with the same answer, there's a good chance that might be a path you want to take. All right, so get lots of research from good sources that we know weren't just made up. All right, step 3, make a hypothesis. So this is where we start getting into you're creating something. So we asked a question, how can I make my tomato plant grow? I did my research, people are saying, brand A of fertilizer, Gatorade, salt water. Okay? A hypothesis is what you think the answer to the question is. All right, so I go back to my question, what's going to make my tomato plant grow better? The only requirements for a hypothesis is it has to be a statement that answers your question, and you have to be able to test it. So my general format, if I water my tomato with salt water, then it will grow more because salt is an important nutrient for living things. All right. Your general format is if, then, because. If I change something, then this will happen because XYZ. Does it have to be if, then, because? No. It just has to be a statement, and you have to be able to test it. I can give my tomato plants salt water, and I can measure if they grow more. That's totally doable. All right. So let's do a quick little check on that. See if we can figure these out. You don't have to write these down, but I want you to answer, are these hypotheses or not? And if they're not, why are they not? All right. So we have our first one. Higher oxygen levels lead to less lice in trout. Is that a hypothesis? The answer is yes, it is. Because this is a statement. It is an answer to a question. So you could say the question could be, how do oxygen levels affect lice in trout? And you could test it. I could put trout in different tanks. I could pump one full of oxygen. The other one has less. And then I could count how many lice there are. Totally doable. Second one. Does chocolate cause acne breakouts? Okay. This is not a hypothesis. What is it? This is a question. This is a good first step. Could we turn this into a hypothesis? We could. All we have to do is make an answer to this. So change this question to a statement. Chocolate causes acne breakouts. Why am I saying that wrong? All right, cool. And you could test that, no problem. All right, so this is a good question, but not a good hypothesis. This is my favorite one. Aliens constructed the Great Pyramids of Giza. Aliens. All right, is this a statement? It is. Does it answer a question? It does. Who constructed the Great Pyramids of Giza? But what's the problem, friends? The problem is you can't test this. There's no feasible way with the resources at my disposal that we can go back in time, 4,000 years and figure out, these things from different planets made the pyramid. No, you can't do that. So it's not a hypothesis. This is not good science. This is bad science. Not good. It's not even science. It's just bad. No. All right. And our last statement, yeast will produce carbon dioxide in the presence of sugar. Is it a statement? It is. Does it answer a question? It does. Will yeast produce carbon dioxide in the presence of sugar? Can you test it? Yes. You could put yeast with some sugar, throw a balloon on it, see if carbon dioxide comes out. So this is a good hypothesis. It's a good biology hypothesis. All right, cool. So let's move on to step 4. Step 4. This is the fun part of science. This is the part of science that everybody likes to focus on. And it's an important step. We need it, but not the only step. We use an experiment to test a hypothesis. So we had to have a question in order to guide our research. We had to do our research so we could find out what other people said, and that helped us make a hypothesis. We need a hypothesis so we know what we are looking for in our experiment. The experiment tests the hypothesis. This is going to tell us what the answer is to our question. It's exciting. Okay? I'm not going to get into the meat and potatoes of the experimental design today. That will be tomorrow when we all see each other on the Zoom. But in an experiment, the experimenter, that would be you, changes one thing. You change the independent variable. And then you measure how that changes another aspect, a dependent variable. Okay? So I could, going back to my tomatoes. I love tomatoes. All right, I had a question. What can I give my tomatoes to make them grow more? I did my research. I found what other people said. I made a hypothesis. If I give my tomatoes salt water, they will grow more. All right, now I do my experiment. I take my tomato plant, and I'm going to take actually 2, but we'll get to that tomorrow, and I'm going to give it some salt water, and then I'm going to measure the growth. Easy squeezy. Number 5. So I've done my experiment. I did the fun part. This part is fun to me, but some people don't think so. We analyze data. This is step 5. We are analyzing data to turn our experiment numbers, the numbers we got in our experiment, into a picture that makes sense. Okay? So we have 2 graphs here. We have this set of data and this set of data. Data can be quantitative or qualitative. We talked about that on Friday. Remember, quantitative, quantities, numbers. Qualitative, qualities or categories. Okay? So let's take a look at these 2 graphs just for funsies, and just do a quick check on if they have their tails. Remember, all graphs need tails. Okay? Do they have titles? Yep. And this graph is about plants and shade and sunlight. This graph is about temperature. Do they have 2 axes, a y and an x? Yep. Here's my y. Remember the yucky x-rays? Same here. Are the intervals evenly spaced? If I look at my plant graph, I see it started at 0 here and goes 10, 20, 30. Okay, it's going by tens. That's good. This one over here, yep, 10, 20, 30. That's going by tens. And the intervals down here are also spaced evenly. So we have 5 a.m. to 8 a.m., then 8 a.m. to 11 a.m., 11 a.m. to 2 p.m. Those are 3-hour intervals. It checks out. Do they have labels with units? With units, okay? This one does. This is good. Temperature in degrees Fahrenheit. That's a good thing to have Fahrenheit there, because the difference between 40 degrees Fahrenheit and 40 degrees Celsius is a really big difference. All right. This one, we also have our labels. We have sun exposure. That's a category. That's why this is a bar graph. These aren't numbers. And we have growth rate. Now, the only thing about this graph I'm not big on, I don't know what they mean by growth rate. Is this a percentage over time? Is this, centimeters per week? I don't know. So this could have a unit. That would be helpful. And lastly, size. Is the size good on these? Yep, this takes up the whole space. This, it does okay. It uses the entirety of the x-axis. You have kind of a little empty space down here. But you could fix that by either doing like a break where you have like a little squiggly line here and you start, instead of starting at 0, you start at a different number like 30 and then you go 40, 50, 60. But it's okay. These are pretty okay graphs. All right. So I need to analyze my data so I can see what my results were. And that's going to help me with my last step, my conclusion. Data will either support or reject a hypothesis. When we make a conclusion, you will say one of these two things. The data supported the hypothesis, or the data rejected the hypothesis. That just means, did it match what you thought was going to happen? Okay, so going back to my tomato example. Okay, I asked my question, what can I give my tomatoes to make them grow more? I did my research. I made a hypothesis. I said salt water will make them grow more. I did my experiment. I watered my little tomato plant, and I took measurements every day. Okay, going back to graphing for a second, I could turn that into a line graph. I could say days down here and then growth, and I could see, did it go up or did it go down? My conclusion is going to be based on my analysis, all right? So I watered my little my plants with salt water. I graphed the data. But it turns out, pals, that at the end of the week, my tomato plant hadn't grown at all. In fact, it had gotten smaller, all right? My data did not match my hypothesis. I thought salt water would make it grow faster, but it ended up shrinking. It ended up not doing what I thought it was going to do. I would reject my hypothesis. Now, is it a bad thing to reject a hypothesis? Does that mean you are a bad science person? No, absolutely not. All right, science is not in the business of right and wrong. It's in the business of finding what is reality. Okay, so if you do an experiment and it doesn't turn out the way you think it's going to, that's okay. It's not a big deal. You did science. It's good. It's all good. Okay, fantastic. And our last step, you do it all over. You repeat. You do it again. All right. I like this little cartoon. I saw it years ago, and I thought it was just adorable and kind of hilarious. So we have this little stick figure man. He pulls the lever. He gets zapped by a little lightning bolt thingy. And he's like, oh, dear, what just happened? You know, normally you'd be like, oh, I learned my lesson. I won't do that. But if you're a science person, you're going to say, does that happen every time? We repeat experiments to see if I get the same results. All right? The more you experiment, the more you repeat and repeat. If you end up getting the same results over and over again, that means there's a greater chance that your answer is valid or true. It is what you think it is. So that's why we have to repeat. All right, so science really technically never ends. Like once you start, you can't stop. You'll make more questions. And that's okay. That's totally okay. That's the cool thing about science, y'all, is it's constantly changing. It's constantly getting new ideas. It's constantly finding out new things. It never stops growing. Kind of like people. It's kind of nice. All right, so that concludes our notes on our scientific method. We went over the 7 steps. We describe what happens in the 7 steps. We know why we have to do them in a particular order. All right, what I would like you to do, all right, if you need to go back and write things down or go back and re-listen to things, that's fine. If you're done with that, think about maybe 1 or 2 questions, observations, things that you would normally say in class or things that you think about this particular set of notes, and we can discuss that tomorrow. After you do that, you have a activity to complete on Canvas, so make sure you do that. And you just let me know if you have any questions that you want to answer before Tuesday. And we'll get back to you, and I will see y'all tomorrow.